General Gaiman and I actually drew straws, and he outranks me, so he gets the final word, and I will give you my remarks. I think there's a third dimension to this conference that needs to be mentioned. It's not just what did you learn and what have you unlearned, but what are the wrong things, perhaps, that you learned that you need to unlearn. And I say that from a perspective as a well, I should have found my stuff on here. There it is. As a young first-line supervisor at NASA, I lived through the Challenger accident. We got that up. And I can tell you right now, I came away with the wrong conclusion from Challenger. Pardon me for having my company logo on it. It comes up because I did it on my company computer and I can't get rid of it, so pardon me. When I was a first-line supervisor in 1986, and I was up in the astronaut office one day having meetings, we took a break out to go down to the corner room, which was a library, and watch the Challenger launch. I thought, okay, we got, 8.5 minutes, 10 minutes, and then we'll be back in here and we'll finish up our checklist review. And of course, it didn't turn out that way. And for the next couple of months, I watched the Rogers Commission do their work, as we all did. And they came out with a report, which we all read, but that was not necessarily what I learned. What I learned from that Challenger launch accident was that a venal, amoral manager made an improper decision and browbeat the troops into that wrong decision and didn't inform his superiors. And for 17 years, I believe that was the cause of the Challenger accident. After the Columbia accident, I heard the CABE talking about this book, The Challenger Launch Decision by Dr. Diane Vaughan out of Boston University, a sociologist, and they kept talking about it and talking about it and talking about it. So I said, I better go read that book. So I went down to the Barnes & Nobles on Merritt Island and found one copy left on the shelf, and I got this big, thick tome, and I read it. And I've got to tell you, I never understood what it meant. I hold 2 degrees in engineering. I never understood what it meant to be an engineer until I read Dr. Vaughan's book. And I certainly did not understand how NASA worked after having been in the organization for, more than a dozen years at that point. I never understood how NASA worked until I read Dr. Vaughan's book. And I think about some of the courses that they taught me in engineering school. I had to take, most memorably, a class on how to solve solutions to series of nonlinear partial differential equations. Now that is a skill that I have never needed in my career ever since. And if I could take that 3 hours back and have a study of sociology, or have a study of psychology, or study of organizational dynamics, that would have been much better use of my time. Let me remind you what Dr. Vaughan analyzed the Challenger launch decision. She said it can truly be said that the Challenger launch decision was a rule-based decision. It was not amorally calculating managers violating rules that were responsible for the tragedy. It was conformity. They were following the rules. And I never knew that. I had come to a wrong conclusion. And one of the things that came out of that wrong conclusion was that we were basically on the right track. We knew what we were doing. And all we had to do was watch out for the one lone wolf guy who was off, getting carried away by schedule pressure. It was not that, it was the whole culture. It was the whole culture. It wasn't necessarily schedule pressure or money things, those contributed, but it was this feeling that we had a mature system. We understood how it was going to operate. We understood the boundaries in which it was going to operate. We did investigate a lot of failures and a lot of in-flight anomalies, but they were relatively trivial. Oh, the Bistro balls was a high potential problem, but we thought we basically understood what was going on. And therefore, that allowed us to be trapped into not paying enough attention to that 4-letter F word, foam, okay? But before we get into that, I wanted to spend just a few minutes because we've heard an awful lot about high reliability organizations, another term that I had never heard in my engineering career at NASA before the mid-2003, high reliability organizations. May come as a shock to you, but what did you study in school? What did you study at work? You know, in my line of work as a flight director, going to seminars was frowned upon. It was thought to be a distraction from the real operational work. So we didn't study on these things. Okay, so let's review what a high reliability organization does. I think if you read the literature, there's 6 principles. High reliability organization is preoccupied with what I would add, the possibility of failure. It's a learning organization. It's reluctant to simplify interpretations. It's sensitive to operations, committed to resilience or defense in depth, and deferential to expertise. We were not doing any of those things before Columbia. Now I have this nice poster which has got kind of everything that's happened in human spaceflight since 1960 all on one page, all the close calls, all the accidents, all there on one page with links that will lead you to, you know, more in-depth discussion. Out of 300 flights-ish, that's a lot of stuff. And the question is, are we learning from it? We got these great lessons learned databases at NASA that nobody ever reads. But now that we can talk about how things fit in context, I think maybe we are becoming a high reliability organization that studies from the past mistakes. I want to take just a second because we tend to talk about space flight as though it was easy, and I know some of you are going to say, oh, this is another one of these discussions about how space flight is hard, but I think it's important to frame the situation that we're working in. You know, Captain Yang, who I have a great deal of respect for, always summed up space flight, shuttle, but it applies to other space flight as well, as we're going to put 7 people on top of 6 million pounds of high explosives, light that fuse, send them 100 miles high in the sky at a speed of 7 times a rifle bullet. What part of that sounds safe to you? I wanted to spend just a second talking about this mythos that we're going to make spaceflight like aviation, at least in the near term. I flew out here on the most popular airliner in service in the world today, Boeing 737. Thank you very much. You've probably flown them yourself. The reason I picked this is because it's roughly the same size as the Space Shuttle Orbiter. And I've got a few statistics here. If you load up a 737 full, it's about 1/3 of its fuel. About 1/3 of it is the crew, baggage, which you had to pay money for, and then about 40% of it is the structure of the vehicle. The FAA requires, last time I checked, a 45-minute fuel reserve for loitering and enough fuel then to divert to an alternate airfield if you get to the place and say the weather got bad. The total shuttle launch weighed 4.5 million pounds, of which 85% is propellant, about 14% is vehicle structure, and about 1.5% is the payload. That's pretty typical for orbital space launch vehicles. The propellant reserve at main engine cutoff for the space shuttle was 0.06% of the total load, or about 1/3 of a second of runtime on the main engines. That's the standard way to get to orbit. That's the reserve you've got to work with. And as a matter of fact, as the little graph shows, for most of the flights we cut off when the propellant level is in the standpipe coming down from the tank actually being empty. Well, let's do a little high school physics. You remember high school physics? Potential and kinetic energy, potential energy mass times altitude. I had to have one of my NASA interns do the math for me because I became a manager. And kinetic energy, 1/2 mass times the velocity squared. So if you're in an airliner cruising at 30,000 feet, about 5 nautical miles high at 500 miles per hour, compare that to a spacecraft 100 nautical miles high going orbital velocity. For the same mass, the altitude difference is 20 times, so it's 20 times harder just to get to the altitude. The potential energy, therefore, is 20 times more, but the kinetic energy goes as the velocity squared. The kinetic energy is 1,000 times greater. It's 1,000 times more energy to be in Earth orbit than to be flying around in a commercial airliner. Or I've got a little graph here that looks at kilojoules per kilogram if you speak metric. There you are if you're flying on a commercial aircraft, the world's fastest military aircraft, Spaceship One on its suborbital hop, the X-15 at its highest and fastest Mercury Redstone. How about any vehicle in Earth orbit? It's a tough problem. Leads to low margins. Reentry, I'm not going to go through the math here in the interest of time, but I'll just tell you that 99% of the energy that comes out of the vehicle during the return to Earth is taken out by air friction. And here we have Columbia and Happier Days piloted by Eileen Collins coming over Houston, and we can see them doing Mach 15 with the thermal shock, the boundary layer 9 millimeters in front of the wing leading edge, 14,000 degrees Fahrenheit, hotter than the visible surface of the sun for about half an hour. That's the kind of problem. And that's just to come back from Earth orbit. If you want to come back from Mars or the moon or someplace, it's an even tougher problem. So that is the problem ahead of us. As I said, I learned a lot from Dr. Vaughan's book. And one of the things that she said in chapter 6 there, the messy interior of engineering practice, which after the accident always looks like an accident waiting to happen, is nothing more than normal technology. Normal technology is unruly, which is to say, not unruly like a 5-year-old child, but comes without a set of rules, because the rule book has to be put together. In the bottom quotation, again from her book, practices don't follow rules. Rules follow evolving practices. In the implementation and operation of complex technological systems, new rules and relationships are continually being reinvented and being invented and negotiated. That's how engineering works. Well, when Bill Parsons and I, thank you, Bill, for picking me. I really don't know why. We had a tough job on our hands. And the first thing that we knew that we had to do to get the space shuttle back to fly was to keep the foam on the vehicle. There's 4,000 pounds of foam on the surface of the external tank, primarily to keep ice from building up. Everybody could tell that if you had ice fall off the tank, that would be really bad. We started talking to the people in the tank, and they said, well, what's the smallest piece or what's the largest piece that we can have come off the tank? And we did a bunch of analysis, and we came out with the answer that if coming off at the worst location, at the worst time, striking the most vulnerable area of the shuttle, you could bring a shuttle down with a piece of foam that weighed about half an ounce and was about the size of a deck of playing cards. And they said, we can't guarantee you'll keep all that foam on the tank. So we said, well, our primary hazard control was going to be the elimination of critical debris. We're going to call it the reduction of critical debris. And then Nancy Curry came up with the next 4 layers for us that allowed us to have some semblance of a fig leaf of a rationale to go fly, one of which was to be able to detect that we'd had a problem through both ascent means, cameras and wing leading edge sensors, and then the rotation pitch maneuver on orbit where we could inspect the heat shield. Then we had tile repair and RCC repair. Now, when we started this little journey, we had numerous experts come to us and tell us that tile repair on orbit was impossible. And in fact, in the 1970s, they did try very hard to develop on-orbit tile repair and failed. And so we flew for, 22 years with no way to repair the heat shield if it was damaged in orbit. It was just an accepted risk. I remember Dr. Kraft came to us and said, there's 2 things you should never do. Never attempt to do tile repair, it's impossible, and never change the outer mold line of the vehicle. And we did both of them. And it cost a lot of money to do both of them and took a lot of time. We came up with repair, and finally, if the repair was unsuccessful, we had this wild crew rescue scheme that might have sort of worked if we ever had to call on it. So that was our rationale. So we started off, we said, well, how are we doing in reducing the risk? Somebody did a calculation, which you don't really believe, that said about 20% of the total risk in flying a shuttle was due to, damage to the thermal protection system. And let's see how we did. Well, in a qualitative, not quantitative way, we have eliminated a lot of the ascent debris. We've added on-orbit inspection repair. We've added this crew rescue capability. But you know what? We really haven't done anything about the rest of this blue, the other 80% of the risk. So what are we going to do about that? Well, we're going to enhance systems engineering and integration. We're going to add an enhancement to safety and mission assurance. We're going to do culture change, and you've heard Bill talk about that a little bit. And then we're going to do some fixes, some deferred maintenance that had been just neglected. But at the end of the day, we were left with significant risk flying the shuttle. And you have to kind of decide, is the reward versus the risk? So maybe 50%, maybe 60% of the risk remained after everything we did after 2.5 years. I want to say a word about this culture change business. I went to the Chris Kraft School of Flight Control, and Dr. Kraft was known to remark on more than one occasion, he said, it's not arrogance if you really are that good. I studied under Jay Green. Some of you know Jay Green. I love Jay Green. Jay Green did not suffer fools gladly, or at all. And those were my mentors. And so I had quite a reputation as a flight director of being a hard-nosed, no-nonsense, hard to get along with stickler of a guy. And all of a sudden, Bill Parsons comes to me and he says, we've got to change the culture because that's what DeCabe said we need to do. And you're in charge of helping to change the mission management team culture. And I thought, wow, this is a Nixon going to China moment. However, we were ultimately successful, and the program did fly out successfully, and we completed the International Space Station a year late, but okay, who's counting? And one of my favorite pictures is Tracy Caldwell there looking out the cupola of the International Space Station, a great resource in low Earth orbit, our toehold in the stars, and the space shuttle program flew out safely. So what did we learn? And I got to tell you, sometimes I think what we learn is kind of like the sign. I think we reduce safety to the sign. George is laughing. I've shown you this picture before. If you read the sign, it says, look out, the sign has sharp edges. Be careful. Don't grab the edges of the sign. Those are all true. Those are all good things. But in fine print down at the bottom, it says, also the bridge is out ahead. So I think sometimes we emphasize what is easy over what is really important. Not that we want somebody to get their fingers cut on the sign, but we really need to know that the bridge is out ahead, so we need to be careful. So I made a list, after all this over, 10 things, and I hope I'm not using up too much time here. But my list of 10 lessons that I personally learned and I would offer to take away from this are, number one, it can happen to you. It can happen to you. Just because you're younger or smarter or read history lessons, don't think you won't make mistakes. And events can't get away from you. They will. Nobody's smart enough to avoid all problems. That sliver of fear, the knowledge that the universe is out there waiting for the least lapse and your attention is ready to bite. And that motivation might just help you avoid catastrophe, or perhaps not. Let's hope Dr. Perot is wrong, and that accidents in complex systems are not inevitable or normal. Better yet, let's all work to prove him wrong. The first principle of a high reliability organization is being preoccupied with failure. Be very preoccupied. Second, focus. That's very simple. In the mission controller's credo, it says to always be aware that suddenly and unexpectedly we may find ourselves in a role where our performance has ultimate consequences. Or even better, I'll show you a slide in a minute, a quotation from an RAF captain from 1930, aviation is not in itself inherently dangerous, but to an even greater degree than the sea, it's terribly unforgiving of any carelessness, incapacity, or neglect. You know, life happens. Distractions mount. The probability is one of those critical decisions will come to you in your career. One will come to you in your career. And I will guarantee you it will come to you on a day when you least expect it, when you are most distracted. Focus. The organization is going to fill your time with busy work and bureaucracy. It will. It will. Keep focused on the important issues. Number 3, speak up. Speak up. We had a lot of people saying, well, I was worried about Columbia, but I was afraid to speak up because I'd get fired. Better to ask a foolish question than to allow a mistake to be made. What is the worst that could be happened to you? What is the worst thing that could happen to you if you speak up? Lose your job? Is that the end of the world? Lose the respect of your peers, maybe? That really cuts closer to the matter. Miss out on a promotion? Letting a mistake go unchallenged may have other consequences. Funerals, programs shut down, lifelong regret. Weigh the cost. Make your choice wisely. Speak up rather than to remain silent. If the organization can't stand you speaking up, then it's not your problem, it's the organization's problem. 4th, kind of goes along with the first one, you're not nearly as smart as you think you are. No matter how low you lower that bar, I can say that's probably still true. Remember what your mother taught you. God gave you 1 mouth and 2 ears, so you should listen twice as much as you talk. That was really good advice. You should listen to her. Defer to expertise rather than to leaders. Check your ego at the door. Too many people are so busy passing out their point of view that they will fail to hear the warnings that are coming at them. Listening is not enough. Comprehending and acting are also required. Or again, to quote Captain Young, if you're not a little bit scared, you don't understand what's about to happen. 5, dissension has tremendous value. Charles Wilson, who was the CEO of General Motors in about 1950, had this great quotation that's attributed to him. If we're all in agreement on this matter, on this decision, then I propose we postpone further discussion of this matter until our next meeting and give ourselves time to develop this agreement and perhaps gain some understanding of what this decision is all about. There's always enough time to do it right. If you don't have dissension, then you haven't examined the problem closely enough. If there's not a natural troublemaker in your group, appoint a devil's advocate. Make sure the devil is smart and articulate, just like his namesake. Draw people out, make them participate. Don't let them walk away in silence. 6th, question the conventional wisdom. People in groups tend to agree on courses of action, which as individuals they know are stupid. It's called the Abilene paradox. We're told that flying in the space shuttle was just as safe as flying in a commercial airliner, and so we denied the crew parachutes and pressure suits. Patently and obviously wrong to the most casual observer, such a belief that could only be called stupid. We were told that the shuttle was a mature flying vehicle with few surprises left. We wanted to believe that, even though the truth was right in front of our eyes. This is and always will be a risky business. Challenge conventional wisdom at every turn and look past it for the truth. Number 7, do good work. People thought Gus Grissom was inarticulate. He used to go to factories and he would say, do good work. I think the opposite. I think he got to the crux, the nub, and he said it perfectly and simply. Do good work. There is no room in this field of endeavor for half-hearted efforts or second best. Do it well or don't do it at all. Don't cut corners and don't let your so-called leaders try to bully you into doing less than your best. Don't accept excuses from others either. Number 8, engineering's done with the numbers. Right up here at the University of Maryland, Dr. David Aiken teaches spacecraft design. He's got a set of laws out on the internet, and I think he's exactly right. Engineering is done with the numbers. Analysis without numbers is only an opinion. Not having all the information you need is never a satisfactory excuse for not starting the analysis. Space is a completely unforgiving environment, and if you screw up the engineering, someone will die, and there'll be no partial credit because most of the analysis was right. Remember the motto of the Mission Evaluation Room, which we sometimes forgot. In God we trust, all others bring data. Don't be persuaded by arm-waving or specious arguments lacking foundations in first principles. Number 9, use your imagination. After the Apollo 1 fire, Colonel Frank Borman said that the fire was the result of a failure of imagination. They just couldn't imagine that a ground test could be so hazardous. Keep your eyes fresh, your imagination active, so you can see the possibilities, good and bad, and work accordingly. And last but not least, nothing worthwhile was ever accomplished without risk. James Michener wrote a great book about the Korean War called The Bridges at Tokori. He made a movie out of it. And in the very end of the movie, after several flight crew off this carrier task force had been lost, the admiral is seen pondering, where do we get such people? Where do we get such men who will go put their lives on the line to do this job? People who will do everything and put their whole being on the line for a cause. We are fortunate to be in their presence. Make the risk as small as you possibly can. Then go forward. It seems that someone far wiser than I said once upon a time that safety is very important, and we should always keep safety in front of us, but in exploration, safety is not the most important thing. In exploration, the most important thing is to actually go. You know, as I get older, the world seems more and more inhabited with ghosts from the past, people, places, and things that are no longer with us. I guess that's just a natural consequence of getting older. After the age of 50, this process has seemed to accelerate with frightening speed. But without passing the lessons and memories on to the next generation, important lessons will inevitably be lost, and mistakes will be repeated. Don't let that happen. Be sure to take a solemn pride in your accomplishment, and don't forget those accomplishments. And I'll leave you with that.